Hello and welcome to today's physics lecture now, wherein we shall not be discussing about a circuit is given and how to draw the Phasor diagram. Instead, the Phasor diagram is in front of you. Now you have to decide that what the circuit consists of. Now whether the circuit consists of L or C or R or if combination, then what? First of all, it is said that given for the below Phasor diagram, this one is a Phasor diagram, find out the peak value of the alternating EMF. So first of all, we need to find out the value of alternating EMF, and as we know that the value of the alternating EMF is nothing but simply E0, which is given in the Phasor diagram, right? The second we need to find out is the phase difference between the alternating EMF and the alternating current. So if we see over here that this phasor indicates the alternating current and this phasor indicates the alternating EMF, so obviously the difference of the angle between them will give us the phase difference, right? So this phase difference is nothing but actually this theta, also which is mentioned over here as phi. So this is equals to phi, right? And this I0 is basically making an angle of omega t, which means that we can write over here initially that I could be written as I equals to I0 sine of omega t. From this phasor diagram we can write that. And we can write that the equation for this alternating EMF as E equals to E0 multiplied by sine of omega t. Whether this phi should be added or subtracted with omega t. See, this is the turning of omega t in this direction, and again an angle of phi has been turned on the anticlockwise or the counterclockwise direction. So this phi is in addition to this omega t. So obviously we shall be adding this phi along with it. Right? Now it has also been said to find out the average power over one cycle. Now the average power over one cycle is actually that we need to find out the average power. That means we have to first integrate like the power, instantaneous power from time 0 to capital T, where capital T is the time period, and we need to divide this by the entire time we have sampled it for. So simply, as we know that we have got various formulas for average power, and it has been said that average power is basically equals to the multiplication of the EV or the virtual value of the alternating EMF multiplied by the virtual value of the alternating current multiplied by cos of this phi, cosine of this phi, right? Now until and unless we know that what the circuit is made up of, how can we decide the cos phi or cos phi, which is also known as the power factor? Right? So over here now it has been said again some given constraints that phi is lesser than pi by 2 but is greater than 0. So this angle difference is actually means that it is lesser than pi by 2. Okay? I0, that means the peak value of the alternating current is equals to 100 ampere, and the frequency of this alternating power from the source is equals to 1 divided by 2 pi, right? And tan of inverse is given of 1 by 6 equal to 9.46, and if like L is present, we do not know that whether the inductor is present or not, and if the inductor is present, obviously there will be a self-inductance. If L is present, then the value of the charge that is going through the inductor will be Q equals to 3 multiplied by T square, where T we actually indicate the time, right? And the potential difference across the inductor will be equals to 2 volt. It is also said that if C is present, we do not know whether it is present or not, but if C is present, then the capacitive susceptance is equals to 4. Now, this is one term, capacitive susceptance. We need to understand that what it is, the capacitive susceptance. Right? So, first of all, we shall undergo these things because we do not know actually whether C is present or not. And if C is not present, what is the value of this line? There is no value. No need to go for the analysis of capacitive susceptance. If C is present, we will look at. Now, it is given that this angle is phi. Over here, what we can observe is that here, this E0, this is actually leading, or this leads. And I0, on the other hand, it actually lags. So, this E and I, they are not in phase because this phi, what is being mentioned, is greater than 0. If phi is greater than 0, which means that E and I are not in phase. And if they are not in phase means the R is present, and along with that obviously some other things are present, either L or C or both of them. First thing. Now, if we undergo that, we have seen this kind of equation where, or wherein we have seen that in the Phasor diagram, the alternating EMF is actually leading. Yes. In the case of purely inductive circuit, we have seen as such. Which means that in the situation of the purely inductive circuit, this alternating EMF actually leads. So, there is obviously an L present over there, so L is present, right? But if you could remember over there, it was mentioned that if the E was leading in the case of a purely inductive circuit, at that time the instantaneous value for this, which will represent this E, will be greater than the instantaneous value of I. But is it the case over here? No. Which means that actually the E0 was like this up to some point, which is greater than this I, but somebody from the down actually dragged it to shorten it up. Now, who dragged it? Yes. As simple as that. The total outphase, which means that the total opposite to the L would be because of C. Because we know that if XL or the inductive reactance is present and the inductive capacitance is present, we need to find out the difference between the inductive reactance and the inductive capacitance, right? So obviously there was some inductive capacitance over here for which the EMF for that capacitance, the potential drop across the two plates, actually dragged this down. So L is also present and C is also present. That is the reason why the E of the inductor has been shortened up. So we could say that now C is also present. If C is present, now we have to analyze that what is capacitive susceptance. As we have seen that the reciprocal of the impedance is basically the admittance, or if we take a conductor, there will be some resistance as well as some admittance, right? Which means that the conductor will have some resistance and also it will be having its own conductance. Say for example, in 100%, like if I actually, say for example, the resistance is equals to 2, then what will be my conductance? My conductance over there will be simply equals to 1 by 2, right? Likewise, there was a concept of capacitive reactance, that is XC. And capacitive susceptance is actually the amount what it is going to conduct. So capacitive susceptance is basically, we denote this term by B, and this is the susceptance for capacitive, we denote it by C. So we can write over here that this B C is equals to 1 divided by XC, where XC, as we have seen earlier, is the capacitive reactance, right? Now this BC is being given as 4, which implies that XC is simply equals to 1 by 4, right? Leave the way as it is for the time being. Now, over here, see, it has been said that over here the frequency of the AC supply is equals to 1 divided by 2 pi. And we know that the value of omega is equals to 2 pi f, right? Now let us replace the value of f as 1 divided by 2 pi over here. So we will get it as 2 pi divided by 1 by 2 pi will simply be equals to 1. Right? If omega is equals to 1, and we know that X of C, or the inductive reactance, is equals to L omega. Now if we replace omega as 1, then XL will simply be equals to L, right? Leave the way as it is now. Because over here, see, if L is present, Q equal to 3T square and EL equals to 2V. Are we provided with the value of self-inductance? No. Then what to do? But we know a formula. Over here, see, it is given that EL, or the EMF for this inductor, given as 2 volt. If it is the case, let us perform as we know from the previous lectures that the EMF at the inductor is equals to L multiplied by the d by dt component of I, where I is the alternating current, right? Now again we can deduce it as E be replaced by 2 will be equals to L multiplied by d by dt component of, again the d by dt component of Q. Why? Because we know that current is basically the rate of flow of charge. And what is the charge actually flowing as it has been given in this equation is Q equals to 3T square. So we can take it as 2 equals to L multiplied by the d by dt component of the d by dt of Q, or d by dt of 3T square. It is simply equals to 6T. And again the d by dt of that will leave only 6. So which implies 2 is equals to L multiplied by 6. Right? Now on cross multiplication we can find out the value of L as equals to 1 divided by 3. We have now found out the value for L. Now if this is a value for L, now we can write over here that XL is simply equals to this L. Let us replace the value of L now, is equals to 1 divided by 3. Right? Now over here, in this question, it has also been given that the resistance, that the value of resistance is equals to 1 by 2 ohm or 0.5 ohm. Now if it is given, and we know now that this circuit is basically Lcr circuit, right? We have deduced this is Lcr because seen by this Phasor diagram. And if this is now the Lcr circuit, we have got XL, we have got XC, now we have got R as well. If this R is given, it is pre-given. R equals to 1 divided by 2 like omega, right? Now if it is given over here, we could say that over here E naught is equals to I naught multiplied by under root of R square plus within bracket XL minus XC whole square. Right? We know this equation from the Lcr circuit. Right? So we can now replace the values as such that E naught will be equals to I naught multiplied by under root of this is half, R equals to half, so the square of this half will be simply equals to 1 divided by 4 plus XL is equals to 1 by 3, XC is equals to 1 by 4. So we can say that 1 by 3 minus of 1 by 4 will be equal to 1 by 12. So 1 divided by 12 whole square will give us 1 divided by 144. Right? And now if we solve it again, we shall be getting the equation like I naught multiplied by, so for example, this will 144 taken denominator and then 144 taken outside, so this will simply be 12 and over here under root of 37. If we do perform the calculation, we will be getting this, right? Now over here, if it is said, say for example, if it is, say for example, we take this under root of 37 as equal to 6, because this is very near to 6. Let us take for this example now that under root of 37 is equals to 6. Then over here we will find the value as I naught multiplied by 6 divided by 12. So as we could see that this will be cancelled out, 6 will cancel this 12, leaving only 2 on the denominator side. So now we can say that E naught is basically equals to I naught divided by 2. Which means that E naught is lesser than I naught. Are we approaching in the right direction? Obviously we are. Why? Because see, over here the instantaneous value of E is basically lesser than the instantaneous value of I. So likewise we have also seen over here that the peak value of E is lesser than the peak value of alternating current. So we are basically going and moving in the right direction. Now over here, for the LCR circuit, we know that the tan of this phase difference, or phi, is simply equal to XL minus XC divided by R, which means that the inductive reactance minus the capacitive reactance whole divided by the resistance. Now, what is XL and what is XC? XL is equals to 1 by 3, XC equals to 1 by 4, which means that 1 by 3 minus 1 by 4 will simply fetches the value of 1 divided by 12. Of 1 divided by 12. And on the denominator side, the value of the resistance, as we could see over here, it is 1 by 2. So this will actually fetch us the value of 1 divided by 6, which now implies that phi will basically be equals to the tan inverse of 1 divided by 6, and see over here the value of tan inverse of 1 divided by 6 is simply equal to 9.46 degree, right? So this will be equals to 9.46 degree. So over here we can mention this value of phi now as phi equals to 9.46 degree, right? Now, so what things we have found out? First of all, now we need to find out the peak value of the alternating EMF. Simple. The alternating EMF is simply the half of the peak value of the alternating current. The peak value of the alternating current is 100 ampere. So, we can say that the peak value of the alternating EMF will simply be equals to 100 divided by 2 will be equals to 50 volt. Found out this one, alternating EMF, okay. Found out this one, the phase difference, that is the phi equals to 9.46 degree. Good. Now we have to find out the average power over one cycle. Average power over one cycle. What do we know the formula? It is simply equals to EV, the virtual value of the alternating EMF, multiplied by the IV, that is the virtual value of the alternating current, multiplied by cos phi. What is phi? 9.46 degree. What is the value of cos 9.46 degree? Given? Is it? No. This is not given. Okay, not a problem. Now let us go to the traditional formula then. The traditional formula over here, it indicates that first of all, let us find out the power factor. Power factor. The power factor is basically the true power divided by the apparent power. And over here this one, and what is the apparent power? This is simply under root of R square plus within bracket XL minus XC whole square for this scenario of LCR circuit. Under root of R square plus XL minus XC whole square, this is simply this thing. Now we have deduced this as such that it comes equal to 1 by 2, right? And the value of R, what is it? The value of R is simply equals to half, right? So we can write it as 1 divided by 2 divided by 1 divided by 2, which is simply equals to 1. Now a mismatch arrives. The power factor is equals to 1, which means obviously that this inductor or capacitor, there is a mismatch. Now do not get into that thing. The power factor is basically not equal to 1. It is near equal to 1. Why? See, over here we have taken that the under root of 37 is nearly equal to 6. But is it actually 6? No. So had we taken this exact value, so it would not have been 1.2. Right? In that scenario, this would have been like, this is actually this 1 we have taken. We should also write it as this one is the near about value. The actual value would have been something like 0.987, like this. Right? Now why is it 1? Why the power factor is equals to 1? The power factor is 1 simply because we have taken under root of 37 as near, because this is nearer to 6. Okay? But like, remember one thing, if ever your power factor comes exactly equal to 1, which means that there is no XL on this term. This particular term would be 0 in this case. Right? And if this is 0 in this case, then obviously the value of XL minus XC will be 0, which indicates that XL is equals to XC. Right? Now either it is possible that either XL or XC is equals to 0, which means that there is no inductor or no capacitor in these circumstances. Right? Or else it is possible that this is a case of a resonance. Now what is resonance? We shall be understanding it later. But right now, over here, if you find ever that the power factor is equals to 1, exactly equals to 1, which means that this term would have been 0. Identifying the two possible cases, XL equals to XC, which means that a condition for resonance, or XL is equals to XC is equals to 0, which means no inductor or no capacitor is present over there. Right? So we have found out the power factor near equal to 1. Let us take now this value. Let us take this near value of 1. So, as we know that the average power over one cycle is equals to EV IV multiplied by the power factor, or cos phi, because this power factor is basically cos phi, right? And what is EV or what is IV now? We know that EV is simply equals to E naught, or the peak value of the alternating EMF, divided by under root 2. And also we know that IV, or the effective value or the virtual value of the alternating EMF, is simply equals to I naught, or the peak value of the alternating current, divided by under root 2. Now if we replace these two things with this, we are sure to get it as equals to E naught I naught divided by 2, under root 2 multiplied by under root 2 will be simply equals to 2, multiplied by the power factor. It is taken as 1 in this case, right? So we can say that it is equals to the value of E naught, it is 50, multiplied by the value of I naught, it is equals to 100 ampere, divided by 2, which will simply be equals to, this will come out to be, this will be cancelled out, 2500 watt, right? Or we can say that the average power in this circumstances over one cycle is equals to 2.5 kilowatt. So we did found out the average power over the one cycle, and also in addition to this we have understood the concept of power factor, that if the power factor is exactly equals to 1, you need to get cautious that either L and C both are absent, or XL and XC both will be equal, which means there is a case of a resonance, which we will be studying in the subsequent lectures. Thank you. Hello and welcome to today's physics lecture, wherein we shall be discussing about a complex type of numerical, right? Over here you could see a circuit which has been given, and over in this place there is an alternating EMF is provided, such that it is given that this alternating EMF will have the equation of E as equals to 10 sine omega t. So seeing from this equation we can say that the peak value of this alternating EMF is equal to 10 and the phase difference is equals to omega t, right? At any point of time, say t, right? Now we have to find out with the help of the phasor diagrams that what will be the equation of this I, or the alternating current. The alternating EMF is being given as 10 sine omega t. We need to find out simply the equation for I. Now over here, as we could see that one resistance of 1 ohm is actually connected in parallel with another resistance of 1 ohm, which in turn is connected in series with a capacitor of 1 divided by omega farad, right? And this entire thing is connected in series combination with this 1 ohm resistor and an inductor of 1 divided by omega Henry, right? Now, say for example, if the current I is flowing over here, then obviously this current shall be flowing through this resistor. So this will be I, because we could see no branching over in this region. But as soon as we will see that there is a sort of branching, by applying the laws of the junction rule, we can say that, okay, say for example, an amount of current I1 is passing through this, which obviously shall indicate that an amount of current I2 is passing through the other branch. Obviously this I1 will pass through the entire branch, because over here this capacitor and this resistor are connected in series, and this I2 will flow through this resistor of 1 ohm, and when they again will meet over here, it will be I, because from the junction rule we know that due to the branching of the currents, obviously this I1 plus I2 will be equal to I, right? And this amount of current I, which actually is the alternating current equation we need to find out, will flow through this inductor. So this is all about the circuit diagram. Now to continue with the phasor diagrams, first of all, it is the human psychology to go with the easiest way first. We have to observe over here that where is the complex region. See, this one is connected in parallel to entire this one, and the entire combination of this part is connected in series with this and this. So first of all, we have to divide the circuit in such a way that forget about this left portions and concentrate on this right portions. So we will be left out only with two branches, the branch with I1 current and the branch with I2 current, right? Over in this region of this branch and this branch, we again will see that which is the simplest. We will see that over here there is a capacitor as well as the resistor, but here only resistor is present. Okay, then let us start with the branch having the current of I2, right? So we shall be starting with, first of all, the branch with current I2. Obviously, if an amount of current I2 is flowing through the resistor, which means that there will be a potential drop across this resistor, right? Let us say, for example, term it as V2. So the potential drop across over in this region, let us term it as V2. Now, we can say that this V2 will simply be equal to, by the Ohm's law, that this will be equals to the amount of current that is flowing through this branch multiplied by the resistance that is being offered. The resistance that is being offered is due to this resistor only in this branch and is equals to 1 ohm. So this will be equals to I2 multiplied by 1. So we should get it as that V2 is equals to I2. Okay, not a problem. So now we can understand that over here, whatever the value of V2 will be, that will be equal to I2. Now we need to understand this concept that what V2 equal to I2 means with respect to the phasor diagram. As we have seen earlier, the phasor diagrams say, for example, now we are going to draw the amount of current. Say, for example, this is the amount of current that is equals to I2, right? Now we need to find out the phasor for V2 as well. Now, since there is only a resistor connected over here, and we have seen in the previous lectures that while drawing a phasor diagram, if the current is flowing only through a resistor, the potential drop or the V will be in the same phase as that of the current. So, V2 will lie along the same phasor line of this I2. But what will be the length of the phasor of V2? Simply V2 is equals to I2. So whatever will be the measurement in length of the phasor for I2, that will simply be the same for that of V2. So we can state it as this line is again for V2. So the V2 and I2 are actually overlapping each other, right? So we can say this as V2 as well. Now we have succeeded in understanding this branch having I2 current, that what will be the phasor diagram for this. Now after we have succeeded in this branch, now let us take our concentration to the branch having the current of I1, right? So our next step will be the branch with current I1. Look over there that the branch which is having the current I1, obviously the I1 flows through the capacitor as well as this like resistance or the resistor. Now first of all we need to find out that what is the capacitive reactance due to this capacitor. And as we know that the capacitive reactance, for example, that will be Xc will simply be equals to 1 divided by omega c, where the value of c is being given as 1 divided by omega. So this will be 1 divided by omega multiplied by 1 divided by omega is equals to 1 ohm. So the capacitive reactance for this we can actually state it as like this is equal to 1 ohm, right? Now if this is 1 ohm, which means that the capacitor or it is actually offering the resistance of say 1 ohm, right? So to understand what is the scenario for this branch, let us see the phasor diagram. The phasor diagram for this, it will be say for example over here, first of all we need to see that what will be the current that will be passing through it. Obviously the current that will be passing through the capacitor as well as the resistor will be the same, and that will be equals to I1. So let us first of all draw I1. Say for example this is I1, right? Now for this I1 we need to understand that for separate entities of this capacitor and this resistor what would be the voltage, right, or the potential drop. Now when this I1 is actually passing through this 1 ohm resistor, at that point of time the V, say for example this resistor is R1, the V R1 will simply be equals to, applying the Ohm's law, the current, the amount of current flowing through it, I1 multiplied by the effective resistance, that is 1 ohm. That is equals to I1 multiplied by 1 simply be equals to I1, or we can say that V of R1 is equals to I1. So now I1 is being given over here, and as we have said in the previous case that V2 was equals to I2, so the V2 and the I2 phasors were overlapping each other. Thus, when VR1 is equals to I1, it will also overlap, the VR1 will overlap the I1, and also from the concept you could understand that since this is only the resistor, the phase difference between the VR1 and the I1 will be equals to 0. Or to be precise, they will be in same phase. So this is another phasor which is actually overlapping this I1, and we could say that this is also phasor of VR1. Now we need to find out for this capacitor, right? So the V for the capacitor will simply be equal to, applying again the Ohm's law, the capacitive reactance multiplied by the amount of current that is flowing through it. The capacitive reactance of the XC, which was found out to be 1 ohm multiplied by I1. So I1 multiplied by 1 ohm will simply be equals to I1, which we can say that this will be equals to I1. So we can also say that this VC now, since it is equal to I1, so this VC will also overlap this I1. No. As we have seen in the previous lectures while understanding the phasor diagram for a purely capacitive circuit, we did observe over there that the voltage drop was actually lagging behind the alternating current by a phase difference of pi by 2. So over here, this phasor will be for VC, where obviously this VC length will be equals to I1. So we can say that this length of the phasor and this length of the phasor, they are completely equal. But one thing to understand, that the phase difference between this alternating current and this VC over here at the capacitor will be, the phase difference will be equals to pi by 2. Now applying, say for example, the Pythagorean geometry or trigonometry, or say for example the laws of vector addition, we could find out that what will be the effective voltage for this VR1 and VC, because see over there they are actually connected in series. So the entire, what is the potential drop between this entire capacitor and this resistor over here will simply be equal to the vector addition of their voltages, right, or their potential drop across the individual points. So if we wish to find out by the help of vector addition by the law of parallelogram, obviously we can find it out. They are meeting over here, so the diagonal of this will simply be equal to the addition of the vectors, because the phasors could be treated as vectors for the addition or subtraction. So this will be, say for example, VR1C, right? Now we need to find out that what will be the value of this VR1C, or to be precise, what would be the length of this phasor or the magnitude of VR1C, right? So it could be easily found out by V of R1C will simply be equals to under root of this VR1 square plus this VC square. VR1 square plus VC square. The value of VR1 is equals to I1, the value of VC will be equals to I1, so it will simply come out to be I1 multiplied by under root 2. So the length of the phasor for this VR1C will simply be equals to I1 multiplied by under root 2, right? Now, after finding out, so for example, we can state that this is VR1C is equals to I1 multiplied by under root of 2. Now, another important thing which we need to actually find out is that we know the amount of current that is flowing through this branch was I1. The I1 was leading this potential drop across this capacitor by pi by 2. Over here the I1 was in phase with the voltage drop for this resistor, but what will be the change of phase or the difference of the phase of this I1 and the entire potential drop for this? Now, as the entire potential drop between these 2 points is equals to VR1C, and the amount of alternating current that is flowing is equals to I1, so obviously the angle between them must be treated as the phase difference between I1 and VR1C. Right? Over here, when looking at the phasor diagram, we could simply say that I1 is leading this VR1C. This will obviously be possible if we find out the value of this phi 1 as greater than 0 degrees. Because if it is not so, then obviously whatever we are concluding from this phasor diagram will be wrong. Right? So let us see over here. The value of phi 1 could be measured as the tan inverse of, over here since it is 90 degree, this angle will also be 90 degree, this will also be 90 degree, and this will also be 90 degrees, or pi by 2. So this is the pi by 2. Observing this particular triangle, this is now a right angle triangle. So the phi 1 will be the tan inverse of this one divided by this one. Now what is the value of this one? It is simply equals to BC divided by this, right? And what is the value of this one? It is simply equals to VR1. Now observe minutely over here that VC and VR1 were both actually equal to I1, right? So they will cancel them out, leaving only 1, and the tan inverse of 1 will be actually the angle of phi 1, and the tan inverse 1 is simply equals to pi by 4 or 45 degrees. So we can say that this phi 1 is basically equals to pi by 4. Right? Now, as from the previous lecture, we did work out and find these things, right? By looking at this phi 1 as equals to pi by 4, which obviously means that this is a positive angle. So, whatever the phasor diagram we have made over here is quite correct, because this is a positive value. Had it been any negative value, the phasor diagram which we have made over here would have been wrong, right? So this phi 1 is equals to pi by 4, which in fact we could now say that this I1 is leading this VR1C, or the potential drop across this entire branch. So we can state this one as VR1C. So here the I1 is actually leading the VR1C by an phase of, or an angle of pi by 4. So we can state likewise that I1 leads VR1C by pi by 4, or in other words, this VR1C actually lags behind this I by an angle of pi by 4, right? Now, as we found out the value of XC, or the capacity capacitive reactance, we would also be interested in finding out that what will be the inductive reactance for this inductor. So, to find it out, we know that the inductive reactance will simply be equals to omega multiplied by L, which is equals to omega multiplied by, this is given as 1 divided by omega Henry, so L will become as 1 divided by omega, so this will cancel out, leaving only 1 omega over here, or 1 ohm, right? So we can say this as, this will offer an effective resistance of say 1 ohm. So this is 1 ohm is the inductive reactance. Now, as in the previous lectures, we did actually classify and identify I1 and I2 branches separately and work on them along the Phasor diagram. This was the Phasor diagram for the part of the branch having I2 current, and this one is for this I1 current. And now we shall be dealing into taking this entire part at one go, right? So this entire thing actually will mean that I1 and I2, we are now going to collapse them together, right? First of all, whenever we will see this, it will strike to our mind that since both these are in parallel, obviously the potential drop across their both ends will be the same. Since this branch or say carrying the current I1 and the branch carrying I2 are in parallel, so we can say that V of R1C will simply be equals to V of R or say V2, or we can say it as V2. So we can say over here that since these two are in parallel, V of R1C will simply be equals to V2, and let us say this as V, right? So, for taking this entire thing at one go, we need to devise the Phasor diagram, which is obviously very interesting. It may be noted over here that this was VR1C, or we are actually telling it V. See, this VR1C is over here, and this was V2 over here. But we just concluded that VR1C is simply equal to V2. So, this phasor is actually this one, this V2, right? So, we can draw, this was the VR1C which we found out. Now we found out that VR1C is equals to V2. So, this particular thing will also be V2. From the phasor diagram again we can find out that V2 and I2 were overlapping. So, this phasor will also be the phasor for I2, right? And from this phasor diagram we could understand that I1 is the phasor which is actually leading this phasor, this particular phasor of V by an angle of phi 1, right? So, this is the phasor of I1 or VR1. Right now, we are interested to find out that, see, this is I1 and this is I2. We are very much interested now to find out that what will be the vector summation of I1 and I2. The vector summation of this I1 and I2 will give us a current simply equals to I, because this I current was actually due to the junction rule. It went to over here as I1 and went over in this branch as I2. So now we are interested in finding out the vector addition of this I1 and I2. Obviously, by applying the parallelogram law of vectors, we could find out that they are meeting over at this point, which obviously indicates that this one is the resultant due to the vector addition of I1 and I2, and let us mark it as I1, 2, which will simply be equal to the I, the amount of current which is actually we are destined to find out the equation of, right? Now, to find out what will be the length of the phasor, or to find out the, say for example, the magnitude of this I2, we have to bifurcate this I1 and I2 in two rectangular components, right? Now, for taking the rectangular components into account, obviously we must clearly demarcate the x-axis and the y-axis. Over here, see, if we do take this VR1C or V2, which is obviously these two are equal to V, if we take this V phasor as x-axis, then taking V as x-axis, we wish to find out that what will be the rectangular component for x-axis of I1 as well as I2. After that, what will be the rectangular component along the y-axis of I1 and I2, and simply finding out them, we will be finding out the under or the root over of the x component and the y component squares, right? Let us see it how. If we wish to find out, say for example, I1, 2 on the x-axis, which means we are actually destined for finding it. First of all, this angle between this VR1C and I1 was equals to phi 1 or 45 degree. Which obviously means that I1 to x will be equals to I1 cos of phi 1 plus the I2 is simply lying on this x-axis of V, right? So we could write it as I2 or as I2 cos 0, right? Which obviously it will mean that the value of I1 multiplied by, now what is the value of cos phi 1? Phi 1 as pi by 4, it will simply be equals to 1 divided by under root 2 plus I2 multiplied by 1, because the value of cos 0 is simply equal to 1, right? So we can write it as, now what we could write I1 as? We could write this I1 as equals to VR1, right? Or we could write it better as VR1C divided by under root 2. Let us take this one. VR1 C divided by under root 2 multiplied by 1 divided by under root 2 plus what we can write I2 as? We can simply write I2 as V2. But we know that V2 is simply equals to VR1C. So we can replace both this by simply by V. So we will find this value as equals to V divided by 2 plus V2, which will be 3 by 2 times of V. So this will be the X component of the vector addition for I1 and I2. Likewise, we need to find out the vector addition of this I1 and I2 on the y-axis, which obviously will be on this axis where this and this VR1C will be making an angle of pi by 2. So, we can say it that I of 1, 2 on the y-axis will be equal to now I1 was making an angle of pi 1 with x-axis, so on y-axis it will be as I1 multiplied by sine of phi 1 plus I2 was making an angle of 0 degree with the x-axis, so it will be I2 multiplied by sine of 0, right? Which will be equal to, now what will be the value of sine 0? The value of sine 0 will simply be equal to 0, which means that the I2 multiplied by sine theta, this is the component of I2 on the y-axis, will simply be equal to 0, which obviously it means that I1 now could be replaced as VR1C divided by under root 2, VR1C divided by under root 2 multiplied by the sine of pi by 4 is equals to 1 divided by root 2. So this will simply be equals to, we can write and replace this VR1C as equals to V, right? Is equals to V divided by 2. So to find out actually the I12, we need to find out the I12 on the x-axis component and after that on the y-axis component, and then we need to find out that the I of 12 will simply be equals to under root of I of 12 x whole square plus I of 12 y whole square, which will simply be equals to, this is equals to 3 by 2v, which means 9 divided by 4v square plus, this is simply equals to v divided by 2, which will be equals to 1 divided by 4v square, or it will be equals to, say for example, v root 10 divided by 2. So this will be the value of I12, which actually we did found out, right? So the length of the phasor for this I12 will simply be equals to the V. What is V? The V is actually VR1C or this V2. This is a length multiplied by root over 10 divided by 2. So this will be the length for this I12. Now, we want to find out that what will be the angle difference between this I12 and this, say for example, the V. The I12, it means the I that is flowing through it, and the V is actually the VR1C or the V2. So say for example, this is phi 2. Now kindly observe over here the phi 2, what we are denoting, we have drawn the phasor. Likewise, we could see that, okay, I12 is actually leading. It will be possible if and only if we find that this phi 2 is greater than 0 degrees. First of all. Secondly, our assumption for this vector addition of this I1 and I2 will be correct if and only if this phi 2 is lesser than this phi 1, as we could see in this phasor diagram. So let us find out. To find out phi 2, by applying the laws of trigonometry, we can find it out as that phi 2 will be simply equal to tan inverse of the I12 component of the y-axis, I12 component of the y-axis over in this region divided by the I12 component over the x-axis. I12 over the x-axis. So this will be equals to tan inverse of, if we find out the v1 to y will be equal to v divided by 2 multiplied by 1 by v of 1 by I1 to x. Now what is I1 to x? It is 3 by 2 of v. So multiplied by 2 by 3v. This 2 will cancel out, this v will also cancel out, leaving out only tan inverse of 1 by 3, which is simply equals to 18.43 degrees. Now obviously 18.43 degrees is greater than 0 degrees and is lesser than pi by 4 or 45 degrees. So this phasor diagram what we have drawn over here is quite correct, and it also gives us the information about that this I12 or this I is actually leading this potential drop across this branch carrying I1 or this branch carrying I2. So now we can say that I12 or simply as I, because I12 is the vector addition of this, which is simply equals to this I, leads VR1C or V2 by an angle of 18.43 degrees. So this is the conclusion which we could draw by looking at this phasor diagram, right? Now well, it may be noted that while we were discussing the branch with, say for example, this I1, right? While we were discussing about this branch having this only resistance, obviously the resistance being offered, the effective resistance being offered was equals to 1 ohm. Now, well, you may ask me that what will be the effective resistance that will be offered by this branch carrying the amount of current equals to I1. Obviously, since this is an alternating current and obviously with a resistor there is connected a capacitor with a capacitive reactance is equals to 1 ohm, then we can deduce it by writing that by Ohm's law, the V of R1C will simply be equals to the amount of current that is flowing through the entire units, that is I1, multiplied by the impedance of this branch, right? It could be written as ZR1C. So the impedance of this branch, ZR1C, is basically the effective resistance that is being put to the flow of this I1, right? Now, do we actually need to find out this ZR1 separately? No. If we do actually compare this equation with, say, this particular equation of VR1C as equals to I1 root 2, then we shall say this is as VR1C, this is as I1, and the remaining of root 2 is equals to ZR1C. Then obviously we could say that the impedance for this branch carrying the current of, say, I1 will simply be equal to root over 2 ohm. Right? And the amount of current that is flowing, that is the I, which is obviously the vector addition over here, is equals to V multiplied by root 10 divided by 2 amperes. Right? Now continued from the previous lecture, we were actually solving this illustration, and we did find out this sort of things, right? And in addition to that, there are certain things given that the cos value of, say, 18.43 is this, sine value of 18.43, the value of root 10 we can take it as 3.2, the value of root over 320 we could take it as 17.9, right? Now, see over here, we did find out the value of I12 in this entire thing, right? When the value of I12 will actually pass through the entire impedance of this, like capacitor and this R1 connected in series, and this R2, which is in fact connected with this in parallel, right? So over here, looking from this equation, we can state that I12 multiplied by the impedance due to R1, C, and this R2 will be equals to the potential drop. We can take it, say for example, V of R1C or V of 2, that is simply equals to V. Right? Now replacing the value of I12 over here, we could find out that V root 10 divided by 2 multiplied by this ZR1 CR2 is equals to V. We will see that this V and this V cancel out, leaving behind only ZR1 CR2 as equals to 2 divided by under root of 10. Right? Now, let us give it another equation. Say for example A. Now, we have found out that what will be the impedance for this part of this circuit. Okay. Now, we can say that this is just an impedance of value 2 divided by under root of 10. The current is flowing such that it is flowing through this resistance, then this impedance value of this, and again through this inductor, right? So the phasor diagram in this situation will look like as it was observed previously that this I, the I that will flow through this entire will be I, and through this inductor flowing is I. And what is I? I was simply equals to what we found out over here as I12. So from this phasor we can actually put up the lines as such. say for example this is I, or this is actually I12, right? Over here for this part, this was VR1C, right? And this was V2, but the voltage for both these parts were the same. The potential drop for both these parts were the same. So we can put it likewise. This one, this is the value for VR1C or V2 or simply V, what we are taking it, right? So this one is the I for this one, this entire one, and this one. We found out what will be the voltage for this particular part. We have also found out. Now we wish to find out that what will be the potential drop for this one, this phasor for potential drop, and phasor for the potential drop across this inductor. Now the potential drop across this resistor will be in phase with the current, right? Because this is simple resistor. But the value of the potential drop will simply be equals to I multiplied by the resistance, that is 1. So the length of the phasor of the V for this resistor will be same as that of the I, right? So we can also say that this particular thing is the phasor for V. Say for example we take it as 3 for V3, and this one let us take as R3. So VR3, this one is the phasor, the same one, right, of the same length. Now for the inductor, as we have seen previously in the lectures, that the voltage leads the current by pi by 2. So over here we could make it, if this is the voltage, it leads the current, this is the current which is flowing I, so the voltage of this shall lead like this. So this is basically VL, where this one is the L, this one is the C, right? Now there are some certain things to observe, that what will be the value of this V? The value of this V will simply be equal to what is the total impedance for this and the amount of current flowing through it. The total impedance is certainly equals to ZR1C R2, that is equals to 2 divided by root 10 multiplied by I, because I is flowing through the entire region, right? Now, this is the case for V. What will be VR3? VR3 will simply be equal to I multiplied by this one, 1 ohm. So this will simply be equals to I. And what will be the value of VL? The value of VL will be equal to the inductive reactance multiplied by the current flowing through it. The current flowing is I, and the inductive reactance is simply equal to 1 ohm. So this will again be is equal to I. Now closely observe that the angle between this I12 or this I and this V was equals to phi 2. So we may change this angle as phi 2. Now, sir, for example, if we are going to treat this I line as x-axis, then obviously we can find out this one is C. This one is for VR1C or V2. This one is for VR3, and this one is for VL. So we can actually find out the x and y components of these three potential drop across this one, and this entire one, right? So taking I as x-axis, we can find out that, say for example, we represent this entire potential drop as, say for example, E. So say for example we represent this as E1, then the E1x will simply be equal to, see, this one and this one over here, they are making 90 degree. But this angle phi 2 is far again beyond. We know that if we are taking their angles in a counterclockwise direction, then obviously we could take it in a positive. But over here, if we are actually coming to the x-axis, over here, like, see, this is the x-axis and it is going in the clockwise direction. This has moved, this V has moved in the clockwise direction. So we have to treat this phi 2 as equal to minus phi 2, right? But over here from I, see that this VL is coming in counterclockwise direction. So we can treat this pi by 2, this angle pi by 2 as equals to plus pi by 2, right? So E1x will simply be equal to, over here, this value of VR3, that is I, because it is actually lying on this axis, plus VL cos 90 or cos pi by 2, plus again V, this one term V multiplied by cos of minus pi by 2, cos of minus pi 2, right? This is minus pi 2. Now from trigonometry we know that the value of cos minus theta is simply equals to cos theta, right? But the value of cos pi by 2 is simply equal to 0. So we need not to worry about this term. So right now we can find out that this E1x will be equal to I plus, what is the value of this V? 2 by under root 10. 2 divided by under root 10 multiplied by the cos of pi by 2. Now what is the value of cos of pi by 2? That is pi 2 is 18.43, right? This is pi 2, this is 18.43, this pi 2. So the value of cos is 0.95 multiplied by 0.95. If we actually solve this equation, this will turn out to be equals to 1.6 I. Right? Let us give this as equation B. Again, we could find out the E1 at Y, on the y-axis. On the this one is the x-axis, and obviously the y-axis will be this VL. So it will simply be equals to VL plus this one VR3 multiplied by cos pi by 2 plus over here we shall find out this value. This one is over here pi 2. So if we are going to take it on the y-axis, regarding that this angle phi 2 is making with the x-axis, so we shall take the sine component. So this will be V multiplied by the sine component of phi 2. But remember, again, we have to consider this phi 2 as a negative one. And we know that the value of sine minus theta is simply equals to minus sine theta. But this one R3 cos pi by 2, it is simply equals to 0. So this will come out to be the value of VL will simply be equals to I minus this V, or we can replace this V as 2 divided by under root 10 multiplied by I multiplied by sine phi 2. Now what is the value of sine phi 2? The value of sine phi 2 is equal to 0.3 is equal to, say for example, 0.3, and over here we could actually, if we are going to solve this equation roughly, we could find out by putting that root over 10 equals to 3.2, we can find out that this one is equals to 0.8i. Let us give it as equation C. Now, we have found out the E1x and the E1y. We are going to find out the resultant of these three, like this one VL, VR3, and this VR1C or V2. We are going to find out the resultant for this, right? So obviously the resultant shall be E as equals to under root of E1x whole square plus E of 1y whole square. If we are going to find it out, obviously we shall find it like this. I to be taken as common from both there, because there will be I square within the root over. We can take I square common, and after that I outside as 1.6 and over there as 0.8. So this will be 3.2, right? So as it is given over here that root over of 320 is equals to 17.9. So the root over of 3.2 will simply be equals to 1.79. So this will be equals to 1.79 I. Let us give this equation as G. So we found out the value of E, right? The value of E would be somewhere like this. Right? And obviously there shall be a difference of angle which is known as the phase difference, right? Let us denote it by simply as phi. Okay? So if we wish to find out, phi will simply be equals to tan inverse of E1y divided by E1x is equals to tan inverse of, say for example, E1y, this is 0.8i and this is 1.6i, so it will simply be equals to 0.5. Right? Now this is a positive value, 0.5, and this is tan inverse of this. So obviously we are going to get somewhat an angle nearer to 26 degree. Right? So we can state that this phi is equals to 26 degree. Now observe carefully. Whatever this E1x or E1y we did find out this E1 is simply equals to, is applicable for this entire one, isn't it? Right? And this is the phasor diagram for this. Over here we can see at various points that I was leading and over like this, but at the entire last we could see that E is leading now and I lags behind E by an angle of 26 degree. So we can now say that this E1 is basically the E over here. So we can say that I lags behind E by 26 degrees, right? Now we need to find out the equation of the alternating current. That was our main motto, right? Over here, looking at this equation, if we do find out that the value of E1, which now we could say as E, is equals to 1.79I, right? Which obviously means that if we compare this equation with the Ohm's law, then we can find out that E will simply be equals to Z of the circuit, this entire circuit, the impedance of this entire circuit multiplied by I, the current flowing through it, this side, right? Now comparing this, say for example equation E with this equation D, we can find out that the impedance of this circuit is simply equals to 1.79, right? So we can now say that Z, the impedance of this entire circuit, is equals to 1.79, obviously in ohms. Now we need to find out that what will be the equation for I. We had seen that I will simply be equals to I naught multiplied by sine of omega t plus phi. If this was the equation of E, then the equation of I shall look like this. And what will be the value of I naught? The value of I naught will simply be equal to, this is the peak value of this EMF, alternating EMF, 10 divided by this impedance of the circuit, that is 1.79, or we can say as simply as 1.8, right? So we can write the equation of I as I naught is 10 divided by 1.8 multiplied by the sine of omega t plus phi. What is the value of phi? The value of phi is over here is 26 degrees. But who is leading? E is leading. Who is lagging? I is lagging. So, what we are finding out the value of this expression of I, obviously this phi for I, this alternating current will look like minus 26 degrees because I is lagging behind E, right? So this will be minus 26 degrees. So this is the expression for the alternating current that is actually flowing through this circuit, entire this circuit, for which the impedance of this entire circuit measured was 1.79 ohm or simply as 1.8 ohm, and we did find out that this E equals to 10 sine omega t. This E actually leads this I by an angle of 26 degrees, right? Thank you.